So Peter, for starters, what do you think about Hartree Fock?
Hartree Fock is a wonderful method. It's very easy to use. It is fast, not the fastest possible. It has a little bit of interaction in it. It's very easy to explain. You have the single particle picture, you can talk about it. Accuracy is of course very limited, so you should not rely on it. Although you have problems sometimes with convergence. Is it useful? Well, I would say only as a starting point for a more interesting post-Hartree Fock method.
So what is it? Which tier do you put it in?
I put it into C.
C tier. Well, next up is NRG, numerical renormalization group.
The NRG, of course, is an extremely worthwhile method. I mean, there was a Nobel Prize for it, for Wilson. It has a disadvantage, it's not so easy to use. I mean, you have actually to know what it's for. It is very special in the sense that it's a method for single impurity models. It is applied for non-equilibrium, but actually not justified. So you should really just stick to thermodynamic properties of impurity problems. It can be extremely accurate, one of the few methods that really resolve quantum physics. And it's very reliable if applied within the restrictions. So I would say it's a very useful method, fast, accurate, but restricted in the realm where it can be applied, but it's a B.
B. Okay, the big boogeyman, quantum Monte Carlo.
Quantum Monte Carlo is hard to judge because there are so many different methods. It is of course well justified to do bosonic systems where you don't have a fermionic minus sign problem. It can parallelize. Embarrassingly, you can basically fill all large scale computer facilities, and the people in the computer center are happy if it runs with high floating point performance. It can be reliable if you do it for thermodynamic properties. It doesn't really work for real time. You usually have to go to Matsubara frequencies, and then you have the problem with going into real time or real frequencies. It is very useful as a benchmark tool for bosonic systems. It does not really work for fermionic problems. So I would say it's also a B.
On the other end of the spectrum, cluster perturbation theory.
Cluster perturbation theory has one big advantage. It is very simple to understand. It's very simple to implement. It gives you a nice overview of the system. And if you are, let's say, in a phase of a system, so far away from a phase transition, I would say it's the method to use for a correlated system. The accuracy is limited because you have to restrict yourself on small systems, but you can really run it then as a black box, so it's highly reliable. And I would say in that respect, it's useful just to look into bulk properties of system as long as you stay away from the phase transitions. And I would also give it a B.
Okay. Now let's dive into some quantum chemistry and continue with covered cluster singles, doubles.
Oh, this is of course the workhorse you do for multi-reference. I mean, you just take your favorite quantum chemistry package, you just let it run, you get a result, and you just don't care. You just say that's a solution. So it's reliable, it's accurate, it's easy to use. I would give it an A.
80. Sticking with workhorses, density functional theory.
Density functional theory is definitely the most used method in condensed matter and in computational chemistry. It's easy to use. You can always get what you want. It doesn't need many resources. Is it useful? Well, it gives you a nice mapping of your physics problem to the functional that you employed, but I doubt that it really gives you insight, so I rate it with an E.
E.T. You know, D is bottom, but okay, fair enough. Well, speaking of methods that are not easy to use, functional renormalization group.
Functional renormalization group is, in my opinion, a highly underrated method. Of course, it is perturbative, so you should not expect that you explain all the difficult problems, but you have a clear way on what you're doing. You know in which sense your renormalization group is flowing, and you can actually go closer to phase transition than with other methods, except with the NRG. So it is a little bit complicated in the application, because you at least should understand how to use functional integrals and how to represent your original problem in that language. Though still, I would rate it with an B.
The one you've been waiting for, DMRG.
DMRG is, of course, the workhorse for correlated condensed matter physics. It is astonishingly simple to implement. It always gives you results, which is kind of a problem, because it also gives you results when you have your parameters set too low. It is expensive with the resources, but you can get extreme accuracy and beat all the other methods as long as you restrict it to low dimensions, basically meaning one-dimensional systems. But there it can give you results that you cannot achieve with any other method, so it's definitely an S.
S tier. And last, but certainly not least, the HQS Quantum Solver.
The HQS Quantum Solver, of course, is the application that's the most easy to use. You just plug in your problem and it solves it. It is fast. It doesn't take many resources. It's extremely accurate and reliable. I mean, it never failed for me. So it's extremely useful. So this is definitely an S or an S+.
Thank you, Peter.